Welcome to distributed database systems. So the objectives of this, number one, will be to learn the distributed database concepts, advantages and disadvantages of distributed databases, functions and architecture of DDBMS, distributed database design, levels of transparency, comparison criteria for DDBMS. So let's begin. Distributed databases. These are logically interrelated collection of shared data and a description of this data, physically distributed over a computer network. While a distributed DBMS is a software system that permits the management of the distributed database and makes the distribution transparent to users. So this is a collection of logically related shared data split into fragments. Fragments may be replicated. Fragments or replicas are located to sites linked by a communication network. Data at each site is under control of a DBMS. DBMSs handle local applications autonomously. Each DBMS participates in at least one global application. So this is an image of a distributed DBMS. We can see site 1, site 2, site 3, site 4, each connected to databases, and in the middle is a computer network. A centralized database that can be accessed over a computer network. Parallel DBMS, a DBMS running across multiple processors and disks designed to execute operations in parallel whenever possible to improve performance. Based on premise that single processor systems can no longer meet requirements for cost-effective scalability, reliability, and performance, parallel DBMS link multiple smaller machines to achieve same throughput as single larger machines with greater scalability and reliability. So the main architecture for parallel DBMS are shared memory, shared disk, and shared nothing. So we can see here, we have shared memory, whereby there is one memory block there that's being shared. We also have shared disk, whereby the disk is being shared amongst all of them. Then we also have the shared nothing, whereby each and every component is connected to their individual CPUs and memory. Advantages of having a DDBMS. It reflects organizational structure, improves shareability and local autonomy, improves availability, improves reliability, improves performance, economics, and modular growth. Disadvantages: complexity, cost, security, integrity control becomes more difficult, lack of standards, lack of experience, database design is more complex. So there are different types of DDBMS. The first one is homogeneous DDBMS. The second one is heterogeneous DDBMS. For the homogeneous DDBMS, all sites use the same DBMS product. It's much easier to design and manage. Approach provides incremental growth and allows increased performance. For the heterogeneous DDBMS, sites may run different DBMS products with possibly different underlying data models. Occurs when sites have implemented their own databases and integration is considered later. Translation requires to allow for different hardware, different DBMS products, different hardware and different DBMS products. Typical solution is to use gateways. The open group formed a working group to provide specifications that will create a database infrastructure environment where there is a common SQL API that allows client applications to be written that do not need to know the vendor of DBMS they are accessing. Common database protocol that enables DBMS from one vendor to communicate directly with DBMS from another vendor without the need for a gateway. A common network protocol that allows communications between different DBMS. Most ambitious goal is to find a way to enable transactions to span DBMS from different vendors without use of a gateway. The open group has now evolved into the Database Interoperability Consortium and are working on version 3 of Distributed Relational Database Architecture Standard. Multi-database system, MDBS, refers to a DDBMS in which each site maintains complete autonomy. The DBMS that resides transparently on top of existing database and file systems and presents a single database to its users, allows users to access and share data without requiring physical database integration. Unfederated multi-base systems has no local users and federated MDBMS. So a network is interconnected collection of autonomous computers, cables of exchanging information. So we have a local area network intended for connecting computers at the same site. Wide area network used when computers or LANs need to be connected over long distances. One, relatively slow and less reliable than LANs. DDBMS using LAN provides much faster response time than one using WAN. So we have the differences. For one, distances up to thousands of kilometers. It links autonomous computers, networks managed by independent organizations, data rate up to 33.6 kbits. We have complex protocols, use point-to-point routing, use irregular topology, and an error rate of 1:10 power 5. Then for LAN, distances up to a few kilometers, links computers that cooperate in distributed applications, network managed by users, data rate up to 2,500 megabits. Simpler protocol, use broadcast routing, use bus or ring topology, error rate about 1:10 power 9. So the functions of a DDBMS. Expect DDBMS to have at least the functionality of a DBMS and also to have the following functionality: extended communication services, extended data dictionary, distributed query processing, extended concurrency control, extended recovery services. Due to diversity, there is no accepted architecture equivalent to ANSI SPARC 3-level architecture. A reference architecture consists of set of global external schemas, global conception schemas, fragmentation schema and allocation schema, set of schemas for each local DBMS conforming to 3-level ANSI SPARC. Some levels may be missing depending on levels of transparency supported. So here we have a reference architecture for our DDBMS where we see S1, we have global external schema. Then we also have the global conceptual schema, fragmentation schema, allocation schema. Then you have the local mapping schema, and then the local conception schema, then the local internal schema. In DDBMS, GSC is a union of all local conceptual schemas. In FMDBS, GCS is a subset of local conceptual schemas consisting of data that each local system agrees to share. GCS of tightly coupled systems involves integration of either parts of LCs or local external schemas. So federated master database system with no GCS is loosely coupled. So here we have a reference architecture for tightly coupled FMDBS, meaning it has the GCS, which is the global conceptual schema. So we have global external schema, global conceptual schema. Then you can see the local external schema, the local conceptual schema, and the local internal schema heading towards the database. So this is a reference architecture of a tightly coupled FMDBS. Below, we see the components of a DDBMS. In the DDBMS, we have the DC, we have the LDBMS, whereby we have the DC, meaning the data communication component, then the GSC, meaning the global system catalog. Very examinable point. So we have the computer network in between, connecting site 1 and 3. Then we have the GSC, the global system catalog, connected to the DDBMS, and the DC, the data communications component. In the distributed database design, we have 3 key issues. Number 1, fragmentation. Relation may be divided into a number of sub-relations, which are then distributed. Allocation. Each fragment is stored at site with optimal distribution. Replication. Copy of fragment may be maintained at several slides. Definition and allocation of fragments carried out strategically to achieve locality of reference, improved reliability and availability, improved performance, balanced storage capacities and costs, minimal communication costs, involves analyzing most important applications based on quantitative or qualitative information. Quantitative information may include frequency with which an application is run, site from which an application is run, performance criteria for transactions and applications. Qualitative information may include transactions that are executed by applications, types of access, and predicates of read operations. For alternative strategies regarding placement of data, we have centralized, partitioned, or fragmented, complete replication, and selective replication. For the centralized, we have it consisting of single database and DBMS stored at one site with the user distributed across the network. For the partitioned, database partitioned into disjointed fragments, with each fragment being assigned to one site. Complete replication consists of maintaining complete copy of databases at each site. Selective replication, combination of partitioning, replication, and centralization. Comparison of strategies for data distribution, we can see that we have centralized fragment, where for the locality of reference in the centralized sector, it's the lowest, reliability, lowest, performance and satisfactory, storage cost, lowest, communication cost, highest. For fragmented, we have locality of reference being high, reliability low, performance satisfactory, storage cost low, lowest, communication cost low. Now, for complete, we have locality of reference being highest, reliability highest, performance best for read, storage cost highest, and high for updating communication costs. Replication, similarly for selective replication, locality of reference is high, reliability low for item, high for system, performance satisfactory, storage cost average, and communication cost low. So clearly we can see that for complete replication, this is what is having the highest reliability and availability, and therefore being the best for read in terms of performance. So why should we fragment? So we have positive usages. Applications work with views rather than entire relations. Data is stored close to where it is most frequently used. This is in terms of efficiency. Data is not needed by local applications if it is not stored. So we have parallelism. With fragments as units of distributions, transactions can be divided into several subqueries that operate on fragments. And we have security. Data not required by local applications is not stored and so not available to unauthorized users. Then the negatives, we have the performance and integrity. Correctness of fragmentation, 3 correctness rules. Number 1, we have completeness. If relation R is decomposed into fragments R1, R2, and Rn, until Rn, each data item that can be found in R must appear in at least one fragment. Then we also have reconstruction. Must be possible to define a relational operation that will reconstruct R from the fragments. Reconstruction for horizontal fragmentation is union operation and join for vertical. We also have disjointness. If data item Di appears in fragment Ri, then it should not appear in any other fragment. The exception, vertical fragmentation, where primary key attributes must be repeated to allow reconstruction. For horizontal fragmentation, data item is a tuple. For vertical fragmentation, data item is an attribute. Types of fragmentation. There are 4 types: horizontal, vertical, mixed, and derived. Other possibility is no fragmentation. If relation is small and not updated frequently, it may be better not to fragment it. So we have horizontal fragmentation and vertical fragmentation. Consists of a subset of tuples of a relation, defined using selection operation of relational algebra. For example, this strategy is determined by looking at predicates used by transactions, involves finding a set of minimal predicates. A set of predicates is complete if and only if any 2 tuples in the same fragment are referenced with the same probability by any application. Predicate is relevant if there is at least one application that accesses fragments differently. Vertical fragmentation consists of a subset of attributes of a relation, defined using projection operation of relational databases. For example, determined by establishing affinity of one attribute to another. So we have mixed fragmentation, consists of a horizontal fragment that is vertically fragmented or a vertical fragment that is horizontally fragmented, defined using selection and projection operations of relational algebra. A horizontal fragment that is based on horizontal fragmentation of apparent relation ensures that fragments that are frequently joined together are at the same site. So this is derived horizontal fragmentation, defined using semi-join operation of relational algebra. Examples of derived horizontal fragmentation. If relation consists more than one foreign key, need to select one as parent. Choice can be based on fragmentation used most frequently or fragmentation with better join characteristics. Use normal methodology to produce a design for the global relations in distributed database design methodology. Examine topology of system to determine where databases will be located. Analyze the most important transactions and identify appropriateness of horizontal and vertical fragmentation. Decide which relations are not to be fragmented. Examine relations on one side of relationships and determine a suitable fragmentation schema. Relations on many sides may be suitable for derived fragmentation. Transparencies in a DDBMS. Distribution transparency. Number one, we have fragmentation transparency, the highest level of transparency. First, the case when an end user or programmer does not need to know that a database is partitioned. Then we also have location transparency, the ability to access objects without the knowledge of their location. Replication transparency, the ability to create multiple copies of objects without any effect of the replication as seen by applications that use the object. Local mapping transparency, the case when an end user or programmer must specify both the fragment names and their location. Naming transparency exists when a unique name must be provided for each object in the database. Then we have transparencies, part B, transaction transparencies. Number one, concurrency transparency, where concurrency transparency requires that concurrent processes can share objects without interference, giving a user the false impression that he or she has exclusive access to the item. Linear transparency refers to the extent to which errors and subsequent recoveries of hosts and services within the systems are invisible to users and applications. Then we have performance transparency, whereby DBMS transparency refers to the case when the DBMS hides the implementation details from the user. Distribution transparency allows users to perceive databases as single logical entities. If DDBMS exhibits distribution transparency, a user need not to know whether the data is fragmented, the location of the data items, otherwise call this local mapping transparency. With replication transparency, a user is unaware of replication of fragments. So more naming transparency. Each item in a DDB must have a unique name. The DDBMS must ensure that no two sites create a database object with the same name. One solution is to create a central name server. However, this will result in the loss of some local autonomy, the central site being a bottleneck, low availability in the central site field. Alternative solution would be prefix object with identifier of the site that created it. For example, branch created at site S1 might be named S1.branch. Also need to identify each fragment and its copies. Thus, copy 2 of fragment 3 would be S1.branch F3.C2. However, this results in loss of distribution transparency. Therefore, an approach that resolves these problems uses aliases for each database object. Thus, S1.branch.f3.c2 might be known as local branch by users at site S1. The DDBMS has the task of mapping all aliases to the appropriate database objects. Ensure that all distributed transactions maintain distributed database integrity and consistency. Distributed transaction accesses data stored at more than one location. So each transaction is divided into a number of sub-transactions, one for each site such as to be accessed. All transactions must execute independently and be logically consistent. Same fundamental principles as for centralized DBMS. DDBMS must ensure both global and local transactions do not interfere with each other. In IBM's distributed relational database architecture, 4 types of transactions are there: remote request, remote unit of work, distributed unit of work, distributed request. Replication makes concurrency more complex. If a copy of a replicated data item is updated, update must be propagated to all the copies. Could propagate changes as part of the original transaction, making it an atomic operation. However, if one site holding a copy is not reachable, then transaction is delayed until the site is reachable. So we could limit update propagation to only those sites currently available and could allow updates to copies to happen asynchronously. Sometimes after the original update, delaying regaining consistency may range from a few seconds to several hours. DDBMS must ensure atomicity and durability of local transactions, means ensuring that sub-transactions of global transactions either all commits or all aborts. Thus, DDBMS must synchronize global transactions to ensure that all sub-transactions have completed successfully before recording a final commit for global transaction. So DDBMS must perform as if it were a centralized DBMS. DDBMS should not suffer any performance degradation and should determine most cost-effective strategy to execute a request. So we have the distributed query processor, maps data request into ordered sequence of operations on local databases, must consider fragmentation, replication, and allocation schemas. So the DQP has to decide which fragment to access, which copy of a fragment to use, which location to use. DQP produces execution strategy optimized with respect to some cost functions. Typically, costs associated with a distributed request include I/O cost, CPU cost, communication cost. So we have examples of performance transparency. So we have dates, 12 fields of a DDBMS. Fundamental principle. To the user, a distributed system should look exactly like an undistributed system. Local autonomy, no reliance on a central site, continuous operation, location independence, fragmentation independence, replication independence. We also have the distributed query processing, distributed transaction processing, hardware independence, operating system independence, network independence, database independence. The last 4 rules are idealistic. And with that, we come to the end of our presentation.